Okay, now we start with the uplink cellular network's performance. We will see how it is different than the downlink performance, and especially from the point of the techniques and tools required. So this is chapter 8 of the book. As you know, uplink communication refers to the case when mobile users are transmitting to the associated base station. So downlink when the users require some data from the base station, so base station transmitted. Uplink is when mobile user is sending some data to the base station. It can be many times the request for some data, or it can be for example, you are uploading to Dropbox. So in that case, you as a mobile user are transmitting to the selected base station. So in this case also, the users need to associate with a base station depending on the cell they are falling. So every user will again fall in the same base station, and many times it is the same base station which was also allocated a downlink. And there are again many more users than the base stations. So there are many users in each cell. And if multiple users need to transmit at the same time, the base station has to provide different resources to each user so that each user can access the channel at in by some amount. Okay, so we can also have OFDMA here, where each user serves one user at random from a cell in a particular time frequency slot, and this frequency slot can be different for each user. So eventually what happens in a particular frequency time slot or time frequency slot, there is only one user which is active for each cell. It may also happen that if the user density is low, there may be some cells where there is no user in that frequency slot. So in that case, base station, there will not be any user in that cell which is transmitting on that cell. And this will of course reduce the interference. So now we will just describe the system model for uplink. We will assume fading, relay fading, and we will take the power based receive power based association. So there is a cellular network M1. The base station process, the locations of the base stations are Xi's. The location of UEs are YI, which is a PPP with density lambda U, and the base station process is a PPP with density lambda. Now, because it's uplink, we will consider a typical base station at the origin, and there will be multiple users. Each user is connected to some base station to which they are transmitting. This base station will also have one user which is false in itself, and that user will be transmitting to this base station. Let's call it Y. Let's call it Y0. Then there are other base stations or users which are also transmitting to their respective base stations. They will also be interfering to this base station, and the link will have a fading HI. So you can associate this HI to ith user, which is YI. In that case, we will create a marked point process which will have YI in HI. We denote this by psi-m. It's a marked Poisson point process where HI is an independent mark which denote the fading, and which will be exponentially distributed because we are assuming relay fading. Then the power level, which will be denoted for association, is simply the average power which is given by transmit power into Xi minus alpha. So from this we will select the best base station, which is the closest base station to the user, and the instantaneous power would be then this received power into Hi. Now, as we said, we will consider an arbitrary user at Y0, and we will only consider this user will be associated with one time frequency slot. So we will only consider this time frequency slot, because all the users which are transmitting in this frequency slot, only they will be interfering with the selected user Y0. So let's assume the serving base station is located at x0. This 0 index is arbitrary and we select it for the considering user and the associated base station. We'll call this as a tagged base station. Now what will happen? We can take this base station location as 0, and because it's a stationary process, the location does not exactly matter. The distance between the active user and the base station is then x0 minus y0 distance, which is r0. Now for the interference purpose, we will only consider users which are transmitting in the same frequency time slot. The users which are in other frequency slot, they are also transmitting, but they will not interfere with the typical user we are considering. So original users come from a PPP psi, which was density lambda u, but the active users which are selected from this according to the time frequency slot, they will be denoted by psi f, and we call those base station as YIs. Now the distance of these active users which are in psi A, where A denote the active, from the distance of these users from tagged base station 0 is denoted by di, which means di is nothing but norm yi, because base station 0 it has the origin. So distance is yi minus origin. Now this association is performed for each cell. So the users, all the actives, they are associated with some base stations, and all of them are associated in a way such that they connect to the closest base station. So in the ith cell, the ith user yi is there, and it is transmitting to its select associated base station, which is located at xn. So a distance between the ith base station and the ith user is denoted by Ri. Now why do we need this distance? That we will be clear in few moments. Note that for y0, the r0 is equal to the distance of this user from its base station which is origin. So that is again y0, and that is also equal to d0 because d0 is also y0. So in other words, the distance of the user from the associated base station for the 0 index is same as the distance of the user from the origin. Now, just to recall, the original user process 5 was assumed to be PPP. Now, what we did is, in this original PPP, there will be many users in each cell. What we do is, we select one user in each cell and assign it to that time frequency slot, and the other user we do not care of. So once you select these users in each cell, there is some correlation, because in one cell there will be only one user selected. So you can see if the two users fall in the same cell, only one of them will be selected. So of course there is some dependency in the location of users, so this cannot be PPP. This thinning which you are doing to select these active users, that is not independent, because if the neighbor user is selected which is the same cell, then this user will not be selected. So once you do dependent thinning and to get phi A, this is not PPP. So how do we characterize this? Actually, it has been seen that it is very hard to characterize this base UE process, because you have to take one user from each one user. So that also depends on phi, and also it's very hard to characterize. So the one way which people do is we try to approximate this process by a PPP approximation. So you will see that computation of performance for uplink is not as elegant as downlink. In downlink, we did not make these many assumptions because we know what the base station process look like. But here uplink, we have to make many approximation in the process. So this is not exact, this is not that much elegant, but still the approximation is shown to be very accurate in the end. So now just for one example, let's see how this user's process look like. So what we do is first we generate all these base stations which are according to PPP. Then we divide the area into small Voronoi cells. Okay, and this user, you will see all the user will have this base station as the closest one among all other base stations. Now we generate the which is PPP. So you will see lot of users in each cell, and of course some cells will have more user, either because their cell is large or maybe the users are more here. Although the density is uniform, because it's a random process, some and PPP, some cells, the same area may have more base station in a particular realization. Sorry, more users in a particular realization. So each of the cell has many users. Now you will see we will associate these users based on the cell they fall in. So the color here shows this kind of association. So all these yellow users are associated with this base station. All these green users are associated with this base station. So all the users are now divided into different cells. Now what we did is we only selected one user in each cell, and that can be random or depending on some scheduling. For a simple case, we just randomly selected. So now each cell will only have one user. Now if you look like, you can very clearly see that this user process is no longer a PPP. Because once you select one user in a particular area, this means you are doing some kind of correlation. Okay, now we have connected these users to this base station, and then this distance for each user, a base station link, this distance we denote by R. So this can be R1, this can be R2, this can be R3, depending on this. This can also be seen as a mark to each user location. Now one thing to notice here is also these RIs are also not independent. Right? Because these RIs are selected from the same base station process. So if you know there is a user and the base station is here, you know a nearby, if you take a nearby user, you know that the base station of this user cannot be anywhere in this cell. Also it should be in this cell in a way that the closest base station to this user is this, not this. This will put a geometric constraints on where this base station can be. Because there are some location where if this base station lies, then this will not be the typical user, sorry, the associated user, sorry, associated base station for this user. Right? You can see if this user lies here, then this will be the closest base station to this user. So once this is there, then you know the base station cannot be here for this user. So this means this Ri depends on this Rj, and there is some correlation between all of these Ris. So now we will calculate first the density of the active user. Right. So you know that if there are lambda base stations, lambda density for base stations, then the number of receivers is equal to number of transmitters, right? That is easy to see. So it can be seen that a lambda active should also be approximately equal to lambda. Lambda active should be ideally equal to the user density. Okay, why I say approximately? Because this is a PPP with a uniform density. This is not a PPP. Also, some of the base stations may be turned off because there is no other users. That because of that reason there may be some difference in between the two. But moreover, we can see lambda active should be equal, almost equal to this lambda. So we start with this model first. We start the modeling the active users with a PPP phi-A with the density lambda. This is the first potential model we came across. We model it using a PPP with the density lambda. Okay. Again, recall that this in fact psi A is not a PPP. We are just approximating it. So now this PPP users, if we have assumed the active users, then it will be uniformly distributed and they should be anywhere. Okay. But now one thing you can notice that active users cannot be everywhere. How? Because we know where the typical user is, right? The one we are considering, the Y0 and the associated X0. If we know the location of them, then we can easily guess that there are some locations where there cannot be any users, right? How do we characterize this? See, one thing is clear, if the user location is such that it is in the same cell as X0, right? In other words, if the user location is such that it is associated with X0, then only one user of the X0 will be selected in that frequency slot, and Y0 is already selected. It means there cannot be other user cannot be allocated the same time frequency slots. It cannot be active in the same time frequency slot. So it means it should not be in a such situation that this user is also associated with only X0 with X0. So only those users can be active here which are associated with other base stations. So understand this. Let's consider a UE yi at location yi. Okay. So suppose this is where the UE is. Now suppose This is your base station which is located at x0. This is your distance ti, which is equal to norm of x0 minus yi. If you create a ball at the center yi with this radius, which means this ball, then you will see if there is any other base station in this ball, then this base station will be closest to this user yi than this tagged base station. Then this can be an active user. But if there is no base station in this ball, then this tagged base station will be the closest base station to this ui at yi. So this means this user cannot be active. So UE will not be able to transmit if in the same frequency slot, if the tag, if there is a base station, if there is no base station in this slot, because then the tag's base station is its own base station and it is already serving the selected UE, which is at y0. So from this we get one condition that if your Ri, if you take any UE at yi, then Ri is the distance between this user and its serving base station. If that distance is less than the distance of this UE to the tagged base station, then it is fine, because then the serving base station is located closer to the UE than the tagged base station. But if Ri is greater than Di, then that is not possible, because Ri can be maximum equal to Di. If there is no base station in the distance Di, then the tagged base station will be your serving base station. So distinguish the active user base stations from the potentially active users. Right? Remember the potential active users we modeled using a PPP of density lambda. From these users, we will remove some of the active, some of the users which do not satisfy this condition. Okay. So again, these are spatially correlated cases, but we will make a very small approximation. Okay, let's first assign Zi as an indicator which will denote that Ri is less than Di. So if Ri is less than Di for any user I, then it means this user is the active user. Okay, what is the probability that a user is active? Remember, Zi is a Bernoulli random variable. It can only be 1 or 0, and it is 1. It means probability that Ri is less than Di. Ri is less than Di means there is at least one base station which is at Ri distance which is less than the Di from the user yi. So another word, this means probability that there is at least one base station inside the ball with center yi and the radius Ti. Okay, if there is one base station, that will be the serving base station to this yi, and then user can be active, so Zi will be 1. So what is the probability that there is one base station in this ball? That is easy to compute. The probability that there is no base station in a ball of radius r is e to power minus lambda pi r square. Here we are considering the ball of radius di, So probability that there is no base station is e to power minus lambda pi di square. Okay, and remember this di is the distance between the base station, the tagged base station, and the user at yi. So base station is tagged base station is at origin and the user is at yi. So di is nothing but 0 minus yi and naught. So this probability depends on the location yi. Similarly, the probability that there is at least one base station inside is given by this. And that is the probability that z would be equal to 1. So we can thin the process phi a, which is the PPP process, such that only user which has this indicator 1 will be selected and the other base station will be, other user will be removed, only user which have this z equal to 1. Now one thing to notice that this z or zi's, they are all correlated to each other because they are being selected from the same base station process. I mean their selection depends on the same base station process, because from the base station process you create this cell and you select one. So because of that there is some correlation implied in the selected active users. So what will be the resultant density if you thin a process with some z, then and by keeping only those z which are 1, then the density will be equal to original density multiplied by the probability that z is 1. Okay, and z depends on the location y, so the density, resultant density will also depend on y. Okay, so what is this py? That probability that zy is equal to 1, that we have already computed. It is equal to 1 minus e of minus lambda pi di square, and di here is y, so norm of y square. So density would be equal to lambda into this probability, which is 1 minus e to power minus lambda pi norm of y square. So now notice this is a non-homogeneous process. And if you put y equal tending to 0, you will see this is 0, which implies that UE very close to the tagged base station will not be active. I mean will have a very low probability to be active. And that is correct, because if the U is very close to tagged base station, then it will be associated with the tagged base station and then it cannot be active. If V goes to infinity, then this lambda active will goes to lambda, which implies that potentially active UE at a very large distance will always be active. And that's also okay, because the user which is at a very far distance will not be connected to this tagged base station. It will, of course, will have, with a very high probability, will have another base station which is closer to it. In this case, the impact of the typical selected UE condition, because we are conditioning on that, it vanishes as distance increases. Now the thinning which we have done is not independent, right? To see this, we will show that the activity of one user may affect the activity of another user. Like for example, take this two users which are very close to each other. One is UEJ and one is UEI. Now suppose the UEI is active, right? This means there is one base station to this UE at which it is connected to, and that is inside this bulb. Now condition on this UI activity, we have to understand what is the activity of this UIJ. Now suppose there was no UEI, there was only UEJ. In that case, what is the probability that this UEJ will be active? Would be equal to that there is one base station, at least one base station in this ball, and that is given by 1 minus e to power minus lambda pi dj square. But once we know, this means there should be one base station in this ball. Now once the UEI here, UEI is there and active, then having a base station in this ball is not sufficient, right? For example, what if there is a base station here, only one base station, and there is no base station here, right? Then this base station will be associated with this also and this also, and only one of them can be active, and then UEI is active. It means UEJ cannot be active. This means that if there is one base station in this area, then it can be certain that the UEJ will be active. This means that the activity of UI puts some correlation on the activity of UIJ. And because of that, this activity is not independent. So the thinning which is done based on the activity is not independent. So this means the thinning is not independent. Hence, the resultant phi is not a PPP. Okay. What is the actual process? It's very difficult to characterize. That being said, however, we will approximate here with a PPP. And that is purely for tractability because PPP is easier to analyze. But we have to finally prove this in the end or show this that via numerical result, then this approximation does not affect the accuracy by a significant amount. In other words, you have to show that the impact of the correlation between the active UEs in their activity is small. So eventually in the end what we do here is we will approximate the active user point process by a PPP with a non-uniform density which is depends on the location, which is given by this. This is nothing but the retaining probability multiplied by the density of the active users, the potentially active users.